everyone and welcome to my class. So today's topic is ferrites or ferromagnetic materials. So ferrites are basically a combination of antiferromagnetic materials and ferromagnetic materials. Basically, the spins in a ferrite or a ferromagnetic material are antiparallel, just like antiferromagnetic materials. But there exists a spontaneous magnetization in a ferromagnetic material, just like a ferromagnetic material. So it is basically a combination of antiferromagnetism and ferromagnetism. What happens basically is that in a ferrite the spins are antiparallel, but the magnitude of the spins is not same. What happens because of this? Because of this uncompensated antiferromagnetism, the magnetic moment or the net magnetic moment is not zero. There is some value of the magnetic moment because of this uncompensated antiferromagnetism, and that net magnetic moment gives you the spontaneous magnetization. So the uncompensated magnetic moment or magnetic moments are responsible for spontaneous magnetization in ferrites. Now, what kind of materials exhibit ferrimagnetism? Spinels. Spinels are the materials which exhibit ferrimagnetism. By spinels I mean that the materials or compounds which have spinel structure. Now what is a spinel structure? There are two types of spinels: normal spinels and inverse spinels. So basically now we will understand what are spinels. Spinels are compounds of the form A, B2, X4, where A is a divalent cation. That means A2 positive. B is a trivalent cation. That means B3 positive. And X can be oxygen, sulfur or selenium. And this is an anion. So these type of materials which have the formula A, B2, X4 are known as spinels. So what can be the examples of spinels? So for example, Fe3O4, or we can write it as FeO dot Fe2O3. This is a ferrite. Then NiFe2O4, COFe2O4, CuFe2O4, etc. These all have spinel structure and they are all ferrites. As you can see, nickel is a divalent cation, Ni2 plus. Ferrous is a trivalent cation, Fe3 positive, and this is the oxide ion. So we have A, B2, X4. Now from where does this basically formula came? So now we will do the structure of spinels. basically understand that from where does AB2X4 came. So in a spinel, one unit cell of a spinel consists of 8 FCC cells. So there are 8 face-centered cubic cells. And first of all, we come to the oxide ion. Now, what is the position of here? What are the lattice points which oxide ions occupy? So, oxide ions basically occupy all the FCC lattice points. So, we know that in one FCC there are 4 lattice points. So, in 8 FCC cells there will be 8 into 4. That means 32 lattice points. So, oxide ions occupy 32 lattice points. Now, second we come to the A2 positive cation. Now, the A2 positive cations, just like nickel, cobalt and copper, they occupy 1/8 of the octahedral voids. Now, in one FCC unit cell, we have 8 octahedral voids. So, in 8 unit cells, we will have 8 into, and what is the contribution? 1/8 of 8. So, 1/8 into 8. That means 8 lattice points. Therefore, A2 positive cations occupy 8 lattice points. Now we are left with the B3 positive cation. So third is B3 positive cation. Now this occupies, these are tetrahedral voids. Understood. So these are tetrahedral voids. So now we come to B3 positive cations. So B3 positive cations, these occupy half of the octahedral voids. And in one FCC, we have 4 octahedral voids. So number of B3 positive cations become half into 4 into 8. So this becomes 16. So if I want to write down the ratio of A, B and X, then this is, for A2 positive we have 8 lattice points, for oxide ions we have 32, and for B3 positive we have 16. So A is 8. So 8 ratio B is 16 and ratio X, which is 32. So this becomes 1:2:4. So this is from where AB2X4 came. structure of a spinel. Now, if you know the structure of a ferromagnetic material, you can calculate the saturation magnetization of that compound. So now we will do how to calculate the saturation magnetization. Calculation of saturation magnetization. Now take for example, we are given a compound Fe3 positive, Fe2 positive, Fe3 positive and O4. Okay. So what happens is that this is a conventional nomenclature that the ions which are written inside the bracket, these ions occupy the octahedral voids, and which are outside the bracket, these occupy the tetrahedral voids. So first of all, we need to know that how many unpaired spins are present in particular ions. So we have two ions, Fe2 positive and Fe3 positive. So in Fe2 positive, first we come to Fe2 positive. In Fe2 positive, we have 6 3d electrons. You can write down the electronic configuration and you get 6 3d electrons. So if I draw the 3d shell, then 1, 2, 3, 4, 5 and 6. So if I have 6 3d electrons, then I have 4 unpaired electrons, and these will give me 4 into mu b magnetic moment. So this will be the magnetic moment because we have 4 unpaired spins. Next is Fe3 positive. So Fe3 positive has 5 3d electrons. That means 1, 2, 3, 4, 5. So 5 3d electrons, that means 5 unpaired spins. So the net magnetic moment becomes 5 into mu b. Now the total magnetic moment or the net magnetic moment is the octahedral magnetic moment minus the tetrahedral magnetic moment. Now which ions occupy octahedral voids? Fe2 positive plus Fe3 positive. So octahedral magnetic moment becomes 4 mu b plus 5 mu b. So this becomes 9 into mu b. And tetrahedral magnetic moment becomes, only it is because of Fe3 positive ion. So Fe3 positive has 5 into mu b contribution. So the net magnetic moment becomes 9 minus 5. That means 4 into mu b. So this is the saturation magnetization for this particular ferrite. So this is how you can calculate the saturation magnetization if you know how many number of unpaired spins are there in particular ferromagnetic material. So this is all about introduction to ferrites, and in the next lecture we will do the molecular field theory of ferrimagnetism. Thank you for watching.